Tonight, as you settle into the familiar embrace of your bed and feel your eyelids grow heavy, something extraordinary is about to unfold within the quiet sanctuary of your mind. While the world around you fades into darkness and your conscious thoughts begin to drift away like gentle waves retreating from shore, your brain is preparing to embark on one of the most fascinating and essential journeys of your entire day. This is not a time of rest for your neural networks. Instead, it is a period of intense, purposeful activity that will quietly reshape your memories, cleanse your thoughts, and prepare you for tomorrow in ways you never imagined possible. The moment you close your eyes and surrender to sleep's gentle pull, your brain doesn't simply power down like a computer shutting off for the night. Rather, it shifts into an entirely different mode of operation, one that is both ancient and incredibly sophisticated. This nightly transformation has been perfected over millions of years of evolution, creating a process so vital that every animal on Earth, from the smallest insects to the largest mammals, must surrender to its call. Your brain during sleep becomes a master architect, a careful curator, and a diligent housekeeper all at once, working tirelessly while you remain blissfully unaware of its efforts. As you drift toward that peaceful boundary between wakefulness and slumber, your brain begins to orchestrate a symphony of electrical activity that will continue throughout the night. The neurons that have been firing rapidly during your day, processing every sight, sound, touch, and thought, begin to slow their frantic pace. But this slowdown is not random or chaotic. Instead, it follows a precise pattern that has been mapped and studied by neuroscientists for decades, revealing a clockwork precision that governs how your mind transitions from the bustling activity of consciousness to the deep, restorative work of sleep. Within the first few minutes of closing your eyes, even before you would consider yourself truly asleep, remarkable changes begin cascading through your brain. The visual cortex, which has been constantly processing the flood of information from your eyes, starts to quiet down as the absence of light signals trigger the release of melatonin from your pineal gland. This small pine cone-shaped structure deep within your brain serves as your body's master timekeeper, responding to the darkness by flooding your system with this naturally occurring hormone that makes you feel drowsy and relaxed. But melatonin is just the beginning of a complex chemical ballet that unfolds as sleep approaches. Your core body temperature begins to drop slightly, a change so subtle you might not even notice it, but one that signals to every cell in your body that the day's work is coming to an end. Your heart rate slows from its daytime rhythm, and your breathing becomes deeper and more regular. These physiological changes are not mere side effects of falling asleep. They are carefully coordinated preparations that create the optimal conditions for the incredible neural processes that are about to begin. As you transition from wakefulness into the first stage of sleep, your brain waves undergo a dramatic transformation that can be measured and observed using sophisticated equipment. During your waking hours, your brain produces what scientists call beta waves, rapid electrical oscillations that reflect the quick, alert thinking required for daily activities. But as sleep approaches, these fast beta waves give way to slower, more rhythmic patterns called alpha waves, which create a state of relaxed awareness that many people experience as that drowsy, peaceful feeling just before sleep truly takes hold. This first stage of sleep, known to researchers as N1, or non-rapid eye movement stage 1, is a brief but crucial transition period that typically lasts only 5 to 10 minutes. During this time, your brain is performing a delicate balancing act, gradually reducing its responsiveness to the outside world, while maintaining just enough awareness to wake you if necessary. Your muscles begin to relax, though they haven't yet entered the deeper relaxation that will come later. Your thoughts start to become less logical and more dreamlike, though you might not yet realize you're actually falling asleep. It's during this gentle transition that your brain begins one of its most important nightly tasks, the process of memory consolidation. Throughout your day, your brain has been constantly recording experiences, storing them temporarily in a region called the hippocampus, which acts like a temporary holding area for new information. But these memories can't stay there forever. The hippocampus has limited capacity, and if memories remained there indefinitely, they would interfere with your ability to learn and remember new things. So, as you drift deeper into sleep, your brain begins the careful process of sorting through the day's experiences, deciding which memories are worth keeping and which can be safely forgotten. This process happens automatically, without any conscious effort on your part, guided by neural circuits that have been shaped by millions of years of evolution to preserve the information that is most likely to be useful for your survival and well-being. The memories that get selected for long-term storage are gradually transferred from the hippocampus to the outer layers of the brain called the cortex, where they can be stored more permanently. This transfer doesn't happen all at once, but rather through a process of repeated activation, like a musician practicing a difficult passage over and over until it becomes second nature. Your sleeping brain literally replays the neural patterns that were active during important experiences, strengthening the connections between neurons and making those memories more stable and accessible. As you sink deeper into sleep, moving from the light drowsiness of stage 1 into the more substantial rest of stage 2, your brain waves continue to change in fascinating ways. The alpha waves that marked your transition into sleep give way to a mixture of different frequencies, including brief bursts of rapid activity called sleep spindles, and larger, slower waves called K-complexes. These distinctive patterns, which can only occur during sleep, serve as gatekeepers that help protect your slumber from disruption while allowing your brain to continue its vital work. Sleep spindles, those brief 11 to 15 Hz bursts of electrical activity, are generated by a small structure called the thalamus, which sits at the center of your brain like a relay station. These spindles help block sensory information from reaching your cortex, creating a kind of neural firewall that prevents sounds, lights, and other stimuli from waking you up. At the same time, they coordinate with other brain regions to facilitate the memory consolidation process, helping to strengthen the neural pathways that encode your most important experiences. The K-complexes that appear during stage 2 sleep are even more mysterious and impressive. These large, slow waves that last for about a second represent one of the largest electrical events that occur in the healthy human brain. Scientists believe they serve multiple purposes, helping to maintain sleep while also playing a role in memory processing and possibly even in the brain's efforts to clear away metabolic waste that has accumulated during the day. As your night progresses and you move deeper into sleep, your brain enters what researchers call slow wave sleep, or stage 3 non-rapid eye movement sleep. This is when some of the most remarkable and essential processes of the night truly begin. Your brain waves slow down dramatically, producing the large, powerful delta waves that give this stage its name. These waves, which oscillate at less than 4 cycles per second, are so different from waking brain activity that they represent a completely different state of consciousness. During slow-wave sleep, your brain becomes remarkably synchronized. Millions of neurons across different regions begin firing in unison, creating waves of electrical activity that sweep across your cortex like slow, powerful tides. This synchronization is not random, but serves specific purposes that are crucial for your mental and physical health. The slow waves help coordinate the transfer of memories from temporary storage to permanent storage, ensuring that the most important information from your day is preserved for future use. But memory consolidation is just one of the vital functions that occur during deep sleep. Perhaps even more remarkably, this is when your brain engages in a process that scientists have only recently begun to understand: the systematic cleaning and maintenance of neural tissue. Just as your body has a lymphatic system that helps remove waste and toxins from your organs and tissues, your brain has its own specialized cleaning system called the glymphatic system that becomes dramatically more active during deep sleep. This glymphatic system works by increasing the flow of cerebrospinal fluid through the spaces between brain cells, washing away metabolic waste products that have accumulated during the day's neural activity. One of the most important waste products that gets cleared away is a protein called beta amyloid, which has been linked to Alzheimer's disease and other forms of dementia. During deep sleep, the spaces between your brain cells actually expand by up to 60%, allowing cerebrospinal fluid to flow more freely and carry away these potentially harmful substances. The discovery of this brain cleaning process has revolutionized our understanding of why sleep is so essential for long-term brain health. It's not just about feeling rested or consolidating memories, though those functions are certainly important. Sleep literally helps keep your brain clean and healthy by removing the molecular garbage that builds up as a natural byproduct of thinking, learning, and living. This cleaning process is coordinated by the same slow brain waves that facilitate memory consolidation, suggesting that these two vital functions of sleep are intimately connected. As waves of synchronized neural activity sweep across your cortex, they help drive the flow of cerebrospinal fluid, ensuring that waste removal occurs efficiently throughout your brain. It's a process so elegant and essential that disrupting it through sleep deprivation or sleep disorders can have serious consequences for both cognitive function and long-term brain health. The neurons that drive this cleaning process fire in carefully coordinated bursts, creating rhythmic waves that propel fluid through the dense tissue of your brain. When researchers have experimentally silenced specific brain regions so that neurons can't create these rhythmic waves, they find that fresh cerebrospinal fluid cannot flow through those areas and trapped waste cannot be removed. This suggests that the electrical activity of sleep is not just a byproduct of rest, but an active driver of the brain's maintenance and repair systems. As your brain moves through these deeper stages of sleep, it continues to replay and process the experiences of your day, but now in ways that go far beyond simple memory storage. The neural circuits that were active during learning become reactivated in precise sequences, allowing your brain to strengthen important memories while also identifying patterns and connections that might not have been obvious during your waking hours. This process can lead to insights and creative solutions that seem to appear out of nowhere when you wake up, as if your sleeping brain has been working on problems in the background while you rested. The remarkable orchestration of your sleeping brain extends far beyond these fundamental cleaning and memory processes. As you settle deeper into the rhythm of slow-wave sleep, your brain begins to engage in what neuroscientists have discovered to be an incredibly sophisticated form of neural rehearsal. The same patterns of brain activity that occurred when you learned something new during the day begin to replay during sleep, but now they unfold in a compressed, accelerated format that allows your brain to practice and refine these neural pathways hundreds of times faster than would be possible during waking hours. This replay phenomenon was first discovered when researchers monitored the brain activity of laboratory animals that had learned to navigate through mazes. They found that during sleep, the exact same sequence of neurons that had fired as the animals moved through the maze would fire again in precisely the same order, as if the animals were mentally retracing their steps through the learned pathway. But even more remarkably, this neural replay occurred at a much faster speed than the original learning, allowing the brain to rehearse the experience multiple times in rapid succession. When scientists began studying this phenomenon in humans, they made an equally fascinating discovery. Using advanced brain monitoring technology, researchers found that people learning new motor skills, such as playing a musical instrument or mastering a complex video game, would literally practice these skills in their sleep. The motor cortex, the region of the brain responsible for controlling movement, would become active during sleep in patterns that exactly matched the neural activity that had occurred during the day's practice session. In essence, your sleeping brain continues to practice and perfect the skills you've been learning working tirelessly to strengthen and refine the neural connections that encode your new abilities. This nocturnal practice session serves multiple purposes that go far beyond simple repetition. As your brain replays these experiences during sleep, it begins to extract the underlying principles and patterns that define skilled performance. Rather than simply memorizing a series of movements or facts, your sleeping brain identifies the deeper rules and relationships that will allow you to apply your new knowledge in novel situations. This process transforms raw experience into genuine understanding, creating flexible, adaptable knowledge that can be used creatively when you encounter similar challenges in the future. The timing of this neural replay is not random, but follows precise patterns that are coordinated with your brain's natural rhythms. The replay tends to occur during specific phases of slow-wave sleep, when your brain waves are most synchronized, suggesting that the large-scale coordination of neural activity creates the optimal conditions for strengthening memory traces. During these moments, your hippocampus, that temporary storage center for new memories, begins to communicate intensively with your cortex, gradually transferring important information to more permanent storage sites throughout your brain. But your sleeping brain doesn't just passively replay the day's experiences. It also engages in a process that scientists call pre-play, where neural circuits become active in patterns that seem to anticipate future experiences. This remarkable phenomenon suggests that your brain is not only processing what has already happened, but is also preparing for what might happen next. By activating neural pathways before you actually need them, your sleeping brain creates a kind of mental scaffolding that will make it easier to learn and adapt when you encounter new situations. This preparation for future learning represents one of the most sophisticated functions of the sleeping brain. As you rest peacefully, your neural networks are essentially running simulations, exploring different possibilities and preparing multiple response patterns that might be useful in various scenarios. This process helps explain why people often wake up with solutions to problems they couldn't solve the day before, or why creative insights seem to emerge spontaneously after a good night's sleep. As your night progresses and you cycle through different stages of sleep, your brain continues to shift between various modes of activity, each serving specific functions in the overall process of neural maintenance and optimization. The transition between different sleep stages is not abrupt, but occurs gradually, with your brain waves slowly changing their frequency and pattern as you move from one phase to another. These transitions are orchestrated by complex interactions between different brain regions, including the brainstem, thalamus, and hypothalamus, which work together to regulate the timing and depth of your sleep. During the lighter stages of non-REM sleep, your brain remains somewhat responsive to the external environment while still engaging in important restorative processes. The thalamus, that relay station we mentioned earlier, continues to filter incoming sensory information, allowing only the most urgent or relevant stimuli to reach your conscious awareness. This selective filtering means that while you might wake up to the sound of your name being called, or an alarm clock, you're likely to sleep through more routine sounds like traffic or the hum of appliances. The sophistication of this filtering system is truly remarkable. Your sleeping brain doesn't simply block all sensory input, but instead performs a complex analysis of incoming information, determining what might be important enough to warrant waking up. A parent will often sleep through loud music or television, but immediately wake to the quiet cry of their infant. This suggests that your brain continues to process and evaluate sensory information even during sleep, maintaining a vigilant watch for anything that might require your attention. As you move deeper into the night, your brain begins to prepare for one of the most fascinating and mysterious phases of sleep: rapid eye movement sleep, commonly known as REM sleep. This stage, which typically occurs in cycles throughout the night with longer and more intense periods toward morning, represents a dramatic shift in brain activity that creates conditions remarkably similar to waking consciousness. During REM sleep, Your brain becomes almost as active as it is when you're awake, yet you remain deeply asleep and largely disconnected from the external world. The transition into REM sleep is marked by distinctive changes throughout your body. Your eyes begin to move rapidly back and forth beneath your closed eyelids, giving this stage its name. Your breathing becomes more irregular, and your heart rate increases. Most remarkably, your voluntary muscles become almost completely paralyzed, a phenomenon that prevents you from acting out the vivid dreams that characterize this stage of sleep. This temporary paralysis is controlled by neurons in your brainstem that actively inhibit the motor neurons responsible for muscle movement, creating a protective mechanism that keeps you safe while your mind explores the rich landscape of dreams. The brain activity during REM sleep is dominated by theta waves, oscillations that occur at a frequency of 4 to 8 cycles per second. These theta waves are associated with deep states of relaxation and creativity, and they create the neurological foundation for the vivid, often bizarre experiences we call dreams. But dreaming is not simply random neural noise or meaningless fantasy. Modern neuroscience has revealed that dreams serve important functions in memory processing, emotional regulation, and creative problem solving. During REM sleep, your brain engages in a different type of memory processing than what occurs during slow-wave sleep. While deep sleep focuses primarily on consolidating factual information and motor skills, REM sleep appears to be particularly important for processing emotional memories and integrating new experiences with existing knowledge. The emotional centers of your brain, including the amygdala and limbic system, become highly active during REM sleep, working to process and regulate the emotional content of your memories. This emotional processing function of REM sleep helps explain why dreams often feature intense emotions and why people sometimes wake from dreams feeling as if they've experienced something profound or meaningful. Your dreaming brain is essentially working through emotional experiences, helping to integrate them with your existing understanding of yourself and the world. This process can lead to new insights and perspectives that weren't available during waking consciousness, as your brain explores novel combinations of memories and emotions without the constraints of logical thinking. The content of dreams reflects this complex interplay between memory consolidation and emotional processing. Dreams often feature elements from recent experiences mixed with older memories, creating new narratives that can seem strange or illogical, but serve important functions in helping your brain organize and make sense of information. The bizarre nature of many dreams reflects the fact that during REM sleep, the logical, analytical parts of your brain are less active, allowing more creative and associative thinking to flourish. But perhaps most remarkably, your dreaming brain doesn't just process existing memories and emotions. It also appears to engage in a form of mental simulation, creating scenarios that allow you to practice responses to challenging or threatening situations in a safe environment. Many dreams feature scenarios where you must overcome obstacles, escape from danger, or solve complex problems. These dream experiences may serve as a form of mental rehearsal, helping to prepare you for similar challenges you might face in waking life. The neural mechanisms that generate dreams involve complex interactions between multiple brain regions. The visual cortex becomes active during dreams, creating the vivid imagery that characterizes many dream experiences. The temporal lobes, which are involved in language and memory, contribute to the narrative structure of dreams. The frontal cortex, while less active than during waking hours, still plays a role in organizing dream content and maintaining some level of narrative coherence. Throughout all these stages of sleep, your brain maintains a delicate balance between different neurotransmitter systems that regulate consciousness, attention, and arousal. Acetylcholine, a neurotransmitter associated with attention and learning, plays a particularly important role in REM sleep, helping to generate the vivid experiences of dreams. Meanwhile, other neurotransmitters like norepinephrine, serotonin, and histamine, which are active during waking hours, are largely suppressed during sleep, allowing your brain to enter these specialized states of consciousness. The regulation of these neurotransmitter systems is controlled by your brain's internal clock, a collection of neurons in the hypothalamus called the suprachiasmatic nucleus. This biological timekeeper responds to light and darkness, coordinating not only when you feel sleepy or alert, but also the timing and intensity of different sleep stages throughout the night. The suprachiasmatic nucleus works in conjunction with the pineal gland to regulate the release of melatonin, ensuring that your sleep-wake cycle remains synchronized with the natural rhythm of day and night. As your night of sleep progresses, you typically cycle through these different stages 4 to 6 times, with each complete cycle lasting approximately 90 minutes. The proportion of time spent in different stages changes throughout the night, with more deep, slow-wave sleep occurring in the first half of the night, and more REM sleep occurring toward morning. This pattern reflects the different functions served by each stage, with the brain prioritizing physical restoration and memory consolidation early in the night, and focusing more on emotional processing and creative integration as morning approaches. The coordination between breathing and brain activity during sleep represents another layer of sophistication in your brain's nightly operations. Recent research has revealed that your breathing rhythm during sleep helps to coordinate the brain waves that strengthen memory consolidation. Just as a conductor coordinates different instruments in an orchestra to produce a symphony, your breathing coordinates hippocampal brain waves that enhance the storage and organization of memories while you sleep. This coordination between breathing and brain waves occurs at remarkably precise intervals, suggesting that the rhythm of respiration serves as a fundamental timing mechanism for neural processes during sleep. The hippocampus, that crucial structure for memory formation, exhibits oscillations that occur at particular points in your breathing cycle, indicating that breathing provides a critical rhythm for proper memory consolidation during sleep. This discovery helps explain why people with sleep-disordered breathing, such as sleep apnea, often experience memory problems and cognitive difficulties. Your sleeping brain also engages in sophisticated processes of memory integration that go far beyond simple storage and retrieval. During sleep, your brain doesn't just file away individual memories like books on a shelf. Instead, it actively works to find connections and relationships between different experiences, weaving them together into a more comprehensive understanding of your world. This process of integration allows your brain to extract general principles and patterns from specific experiences, creating knowledge that is more flexible and useful than isolated facts. The integration of memories during sleep involves complex interactions between the hippocampus and various regions of the cortex. As memories are replayed during sleep, your brain identifies common elements and themes across different experiences, gradually building up abstract representations that capture the essential features of categories of knowledge. This process helps explain how you can recognize a new type of dog you've never seen before, or understand a novel situation based on your past experiences with similar contexts. This nightly reorganization of memory also involves a process of forgetting that is just as important as remembering. Your brain doesn't have unlimited storage capacity, and retaining every detail of every experience would quickly overwhelm your neural systems. During sleep, your brain engages in a selective forgetting process, allowing less important details to fade while strengthening the memories that are most likely to be useful in the future. This process of forgetting is not random, but follows specific patterns that prioritize emotionally significant events and information that is consistent with your existing knowledge and goals. The emotional processing that occurs during sleep serves functions that extend far beyond simple memory consolidation. Your sleeping brain actively works to regulate your emotional responses, helping to reduce the intensity of negative emotions associated with difficult experiences, while preserving the important information those experiences contain. This process can help explain why people often feel better about upsetting events after sleeping on them. and why the phrase sleeping on it has become a common piece of wisdom for dealing with difficult decisions. During REM sleep, your brain appears to engage in a form of emotional problem solving, exploring different ways of understanding and responding to challenging situations. The high levels of activity in emotional brain regions during this stage, combined with the reduced influence of logical constraint, create conditions that allow for new perspectives and insights to emerge. This process can lead to creative solutions and emotional breakthroughs that weren't available during waking consciousness. As morning approaches and your brain begins to prepare for the transition back to wakefulness, the final REM periods of the night often produce the most vivid and memorable dreams. These dreams may serve as a bridge between the night's processing work and the coming day's challenges, integrating the insights and emotional regulation achieved during sleep with the practical demands of conscious life. The gradual lightening of sleep toward morning ensures that you wake naturally and gently, with your brain systems properly coordinated and ready to engage with the world. Throughout this entire nightly journey, your brain has been working with a purpose and sophistication that rivals any conscious activity. While you rested peacefully, unaware of the intricate processes unfolding within your mind, your neural networks have been cleaning, organizing, integrating, and preparing. They have strengthened important memories while allowing others to fade, processed emotions while maintaining psychological balance, and prepared new pathways for tomorrow's learning and growth. This remarkable orchestration happens automatically, guided by millions of years of evolutionary refinement, ensuring that you wake refreshed and ready to face whatever challenges the new day might bring. The remarkable processes we've explored so far represent only the beginning of your brain's nightly transformation. As you move deeper into sleep and your neural networks settle into their specialized rhythms, your brain begins to engage in even more sophisticated operations that will fundamentally reshape how you think, feel, and remember when morning arrives. These processes unfold with a precision that has been refined over countless generations, creating a system so elegant and efficient that it operates flawlessly night after night, year after year, without requiring any conscious oversight from you. One of the most profound discoveries in recent neuroscience research involves understanding how your brain manages the delicate balance between storing new information and maintaining access to older memories. Throughout your waking hours, your hippocampus has been busy encoding new experiences, but this temporary storage system has inherent limitations. If new memories remained in the hippocampus indefinitely, they would eventually interfere with your ability to form fresh memories, creating a kind of neural traffic jam that would impair your learning capacity. To prevent this, your sleeping brain engages in a sophisticated redistribution process that neuroscientists call systems consolidation. During the deeper stages of non-REM sleep, your brain orchestrates a careful dialogue between the hippocampus and various regions of the cortex. The hippocampus begins to replay the neural patterns that were active during important learning experiences, but now these patterns are transmitted to cortical areas that specialize in long-term storage. This transfer doesn't happen all at once, but rather through a gradual process that can take weeks or even months to complete. Each night, as your brain cycles through its various sleep stages, another layer of consolidation occurs, slowly but steadily moving important memories from temporary to permanent storage. This consolidation process is remarkably selective and intelligent. Your sleeping brain doesn't simply transfer every experience indiscriminately. Instead, it evaluates the relative importance of different memories based on factors such as emotional significance, relevance to your goals, and consistency with your existing knowledge. Memories that are deemed most valuable receive the strongest consolidation signals, while less important information is allowed to fade away naturally. This selective process ensures that your long-term memory remains organized and efficient, filled with information that is most likely to be useful in future situations. The neural mechanisms that drive this consolidation process are intricate and beautiful in their complexity. During slow-wave sleep, your brain generates precisely coordinated waves of electrical activity that sweep across the cortex like gentle tides. These waves, which occur roughly once per second, create windows of opportunity during which the hippocampus can communicate effectively with cortical regions. When these slow waves reach their peak, cortical neurons become highly excitable and responsive to input from the hippocampus. During the troughs between waves, cortical activity quiets down, allowing the newly transmitted information to stabilize and integrate with existing memory networks. Nested within these slow waves are faster oscillations called sleep spindles, which we encountered earlier in our journey. These spindles, generated by the thalamus, serve as crucial coordinators in the consolidation process. They help to synchronize activity between different brain regions and appear to gate the flow of information from the hippocampus to the cortex. When sleep spindles occur at precisely the right moment in relation to slow waves, the efficiency of memory consolidation increases dramatically. This temporal coordination represents one of the most elegant examples of neural timing in the entire brain. The consolidation process also involves another type of high-frequency activity called sharp wave ripples, which originate in the hippocampus itself. These brief, intense bursts of neural activity occur when large populations of hippocampal neurons fire in rapid succession, creating ripple-like patterns that can be detected with sensitive recording equipment. During these ripples, the hippocampus replays sequences of neural activity that occurred during learning, but at speeds that are much faster than the original experience. A sequence that took several seconds to unfold during waking might be compressed into just a few milliseconds during a sharp wave ripple. These accelerated replays serve multiple functions in the consolidation process. First, they allow the hippocampus to practice the neural sequences associated with important memories, strengthening the connections between neurons and making the memories more stable. Second, they provide a compressed summary of experience that can be efficiently transmitted to cortical areas for long-term storage. Third, they appear to help the brain identify patterns and relationships between different memories, facilitating the integration of new information with existing knowledge structures. As your brain engages in this nightly reorganization of memory, it also performs another crucial function that has only recently been appreciated by neuroscientists: the active forgetting of information that is no longer needed. This forgetting process is not simply the passive decay of unused memories, but rather an active, energy-requiring process that helps to optimize your brain's storage capacity and retrieval efficiency. During sleep, your brain identifies memories that are redundant, outdated, or inconsistent with more recent information, and it actively weakens the neural connections that support these memories. This targeted forgetting serves several important purposes. It prevents your memory systems from becoming cluttered with obsolete information. It reduces interference between similar memories, and it helps to extract general principles from specific experiences. For example, if you learn a new route to work, your brain will gradually forget the specific details of your old route, while retaining the general knowledge about navigation in your neighborhood. This process of selective forgetting allows your memory to become more efficient and flexible over time. The mechanisms of active forgetting involve many of the same neural systems that participate in memory consolidation, but they operate in reverse. Instead of strengthening synaptic connections, these systems actively weaken connections that support memories targeted for forgetting. This process is mediated by specific neurotransmitters and cellular mechanisms that can selectively modify the strength of individual synapses. The result is a memory system that becomes more refined and efficient with each night of sleep. As we move deeper into the night and your brain continues its cycles through different sleep stages, we encounter periods of REM sleep that become longer and more intense. These REM periods, particularly those that occur in the early morning hours, represent some of the most fascinating and mysterious aspects of the sleeping brain. During these times, your neural activity reaches levels that rival or even exceed those seen during waking consciousness. yet you remain deeply asleep and largely disconnected from the external world. The brain activity during REM sleep is characterized by a unique pattern of neurotransmitter activity that creates conditions unlike any other state of consciousness. The neurons that normally release norepinephrine, serotonin, and histamine, chemicals that promote alertness and logical thinking during waking hours, become almost completely silent. At the same time, neurons that release acetylcholine, a neurotransmitter associated with attention and memory, become highly active. This unusual neurochemical environment creates the perfect conditions for the vivid, emotionally intense, and often bizarre experiences we call dreams. The visual cortex becomes remarkably active during REM sleep, generating the rich imagery that characterizes most dreams. This activity occurs even though your eyes are closed and you're receiving no visual input from the external world. The images in dreams are created entirely by your brain's own activity, drawing from stored visual memories and recombining them in novel ways. The temporal lobes, which process language and narrative, contribute to the story-like quality of dreams, while the limbic system, which processes emotions, imbues dream content with the intense feelings that often accompany dream experiences. One of the most intriguing aspects of REM sleep is the temporary paralysis that prevents you from acting out your dreams. This paralysis is caused by neurons in the brainstem that actively inhibit the motor neurons responsible for voluntary movement. The inhibition is so complete that even the strongest dream actions result in only minimal muscle twitches. This protective mechanism prevents you from potentially injuring yourself or others while your mind explores the uninhibited landscape of dreams. The content and function of dreams have been subjects of fascination and speculation for centuries, but modern neuroscience has begun to reveal some of the important roles that dreaming plays in brain function. Dreams appear to serve as a form of emotional processing, helping your brain to integrate emotionally significant experiences with your existing understanding of yourself and the world. The high activity in emotional brain regions during REM sleep, combined with the reduced influence of logical constraint, creates conditions that allow for novel perspectives and creative insights to emerge. During dreams, your brain often combines elements from recent experiences with older memories in unexpected ways, creating scenarios that can seem strange or illogical, but serve important functions in memory integration. These novel combinations can lead to creative breakthroughs and problem-solving insights that weren't available during conscious thought. Many scientific discoveries and artistic creations have reportedly emerged from dream experiences, suggesting that the unconstrained thinking of REM sleep can generate genuinely useful insights. Dreams also appear to play a role in emotional regulation, helping to process and integrate difficult or traumatic experiences in a safe psychological environment. The intense emotional content of many dreams may reflect your brain's attempts to work through unresolved feelings and conflicts, gradually reducing their emotional impact through repeated processing. This function of dreaming can help explain why people often feel better about upsetting events after sleeping on them, and why disrupted REM sleep is associated with mood disorders and emotional instability. The neural basis of dream generation involves complex interactions between multiple brain regions, each contributing different elements to the overall dream experience. The pons, a structure in the brainstem, appears to initiate REM sleep and coordinate many of its characteristics, including the rapid eye movements that give this stage its name. The thalamus, which normally filters sensory information during waking hours, becomes active during REM sleep, but in a different pattern that may contribute to the hallucinatory quality of dreams. The hippocampus continues to be active during REM sleep, but its role shifts from the memory consolidation functions that dominate slow-wave sleep to a more creative and integrative form of processing. During REM sleep, the hippocampus appears to explore novel combinations of stored memories, creating the bizarre and often impossible scenarios that characterize dream content. This creative recombination of memories may serve important functions in problem solving and adaptation, allowing your brain to explore potential solutions to challenges in a risk-free mental environment. As REM periods progress throughout the night, they tend to become longer and more intense, with the most vivid and memorable dreams typically occurring in the early morning hours. This pattern reflects the natural rhythm of your brain's neurochemical systems and ensures that the important functions of REM sleep are completed before you wake. The gradual increase in REM intensity also helps to prepare your brain for the transition back to waking consciousness, with the final REM period often serving as a bridge between the night's processing work and the coming day's activities. Throughout all these stages of sleep, your brain maintains its remarkable waste clearance system that we explored earlier. The glymphatic system continues to flush metabolic toxins from neural tissue, but its activity varies depending on the sleep stage and the specific brain regions involved. During slow-wave sleep, when neural activity is highly synchronized, the flow of cerebrospinal fluid is particularly efficient, allowing for maximum waste removal from areas that were most active during the day. This waste clearance process is not uniform throughout the brain, but instead follows patterns that reflect the day's activities and the brain regions that were most heavily used. Areas that experienced high levels of activity during waking hours receive more intensive cleaning during sleep, ensuring that the metabolic byproducts of neural activity are efficiently removed. This targeted cleaning helps to maintain the health and function of brain tissue while preparing neural circuits for optimal performance the following day. The coordination between neural activity and waste clearance represents one of the most elegant aspects of sleep physiology. The same slow waves that facilitate memory consolidation also drive the flow of cerebrospinal fluid through brain tissue. This dual function ensures that the brain's maintenance needs are met simultaneously with its information processing requirements, maximizing the efficiency of the sleep period. As your night progresses, your brain also engages in important hormonal regulation that affects your physical health and mental well-being. The deep stages of slow-wave sleep trigger the release of growth hormone, a crucial substance that promotes tissue repair, immune function, and cellular regeneration throughout your body. This hormone is released in pulses that are tightly synchronized with your sleep cycles, with the largest releases occurring during the first few hours of sleep when slow-wave activity is most intense. Growth hormone doesn't just affect physical growth and repair, it also plays important roles in brain function, promoting the synthesis of proteins needed for memory consolidation and neuroplasticity. The timing of growth hormone release during sleep ensures that these important brain maintenance functions occur when they can be most effective, coordinated with the other restorative processes that characterize deep sleep. Your sleeping brain also regulates the production of cortisol, often called the stress hormone, which normally follows a daily rhythm that reaches its lowest levels during the night. This suppression of cortisol during sleep is crucial for both physical and mental health, as chronically elevated cortisol levels can impair immune function, disrupt memory formation, and contribute to mood disorders. The natural decline in cortisol during sleep creates optimal conditions for the restorative processes that occur during this time. The regulation of these hormones is controlled by your brain's master clock in the hypothalamus, which coordinates sleep timing with numerous other physiological processes. This internal timekeeper responds to environmental cues like light and darkness, but it also maintains its own intrinsic rhythm that continues even in the absence of external time signals. The precision of this biological clock ensures that sleep occurs at optimal times, and that the various processes of sleep are properly coordinated with your body's other needs. Temperature regulation during sleep represents another sophisticated aspect of your brain's nightly orchestration. Your core body temperature naturally declines as sleep approaches, and this cooling continues throughout the night, reaching its lowest point in the early morning hours. This temperature drop is not simply a passive consequence of reduced activity, but rather an active process controlled by your hypothalamus that serves important functions in sleep quality and brain maintenance. The cooling of your brain during sleep appears to enhance the efficiency of many neural processes, including memory consolidation and waste clearance. Lower temperatures reduce the metabolic demands of brain tissue and may help to preserve the integrity of neural structures during the intensive processing that occurs during sleep. The temperature cycle also helps to coordinate the timing of different sleep stages, with the deepest sleep typically occurring when brain temperature is at its lowest. Your breathing patterns during sleep undergo their own characteristic changes that reflect the different functions of various sleep stages. During slow-wave sleep, breathing becomes deep and regular, creating optimal conditions for the coordination between respiratory rhythms and brain waves that we discussed earlier. This regular breathing pattern helps to drive the oscillations in cerebrospinal fluid flow that are crucial for brain waste clearance. During REM sleep, breathing becomes more variable and irregular, reflecting the intense and changeable brain activity that characterizes this stage. The breathing irregularity during REM sleep may contribute to the vivid and often chaotic nature of dream experiences, as changes in oxygen and carbon dioxide levels can influence brain activity and consciousness. Despite these irregularities, your brain maintains careful control over breathing to ensure that oxygen delivery remains adequate for the high metabolic demands of REM sleep. The integration of breathing with brain activity during sleep represents one of the most fundamental aspects of sleep physiology. Your respiratory system doesn't simply maintain gas exchange during sleep, but actively participates in the neural processes that make sleep restorative. The rhythm of breathing provides a temporal framework that helps to coordinate various brain activities, ensuring that the complex processes of sleep unfold in their proper sequence and timing. As morning approaches and your final sleep cycles begin, your brain starts to prepare for the transition back to waking consciousness. This preparation involves gradual changes in neurotransmitter activity, hormone levels, and brainwave patterns that ensure you wake up naturally and feel refreshed. The process is so gradual and gentle that you typically remain unaware of it, experiencing only the final moment when consciousness fully returns. The morning awakening process involves the reactivation of the brain systems that maintain alert consciousness during waking hours. Neurons that release norepinephrine, serotonin, and histamine gradually increase their activity, while the acetylcholine systems that dominated REM sleep begin to shift into their waking pattern. This neurochemical transition restores the balance of neurotransmitters needed for focused attention, logical thinking, and interaction with the external world. Your body temperature begins to rise as morning approaches, signaling to every cell that the day's activities are about to begin. This temperature increase is coordinated with increases in cortisol and other activating hormones that help to mobilize your body's resources for the coming day. The timing of these changes is precisely controlled by your biological clock, ensuring that you wake up at the optimal time for your individual circadian rhythm. The final REM periods of the night often produce the most vivid and memorable dreams, and these dreams may serve as a bridge between the night's processing work and the day's upcoming challenges. The content of morning dreams often reflects a synthesis of the emotional and cognitive processing that has occurred throughout the night, providing insights and perspectives that can be helpful in dealing with waking concerns. As consciousness gradually returns, the various systems of your brain begin to shift back into their waking configurations. The thalamus resumes its role as a gatekeeper for sensory information, allowing the sights and sounds of the external world to once again reach your conscious awareness. The prefrontal cortex, which was largely quiet during sleep, reactivates to provide executive control over your thoughts and actions. The motor cortex regains control over voluntary movement, allowing you to stretch, move, and begin the physical activities of the day. The transition from sleep to waking represents one of the most remarkable daily transformations in human physiology. In the space of just a few minutes, your brain shifts from the inwardly focused, maintenance-oriented activity of sleep to the outwardly directed, goal-oriented activity of waking consciousness. This transition is so smooth and natural that you typically take it for granted, yet it represents the culmination of hours of complex neural processing that has prepared your mind for optimal function. The benefits of this nightly neural maintenance extend far beyond simply feeling rested. The memory consolidation that occurs during sleep enhances your ability to learn and remember new information. The emotional processing that takes place during REM sleep improves your psychological resilience and emotional regulation. The waste clearance that happens during deep sleep protects your brain from the accumulation of toxic substances that could impair cognitive function over time. The creative insights that emerge from the unconstrained thinking of REM sleep can lead to innovative solutions and artistic breakthroughs. The hormonal regulation that occurs during sleep supports your immune system, promotes physical growth and repair, and maintains the delicate balance of chemicals that support mental health. The temperature and metabolic changes that characterize sleep optimize the efficiency of countless cellular processes throughout your brain and body. Perhaps most remarkably, all of these complex processes occur automatically, without any conscious effort or awareness on your part. Your brain has evolved sophisticated mechanisms that ensure optimal sleep occurs naturally, guided by internal rhythms and environmental cues that have been refined over millions of years of evolution. The systems that control sleep are so robust and reliable that they continue to function effectively throughout your entire lifetime, adapting to changes in your age, health, and circumstances while maintaining their essential functions. The study of sleep represents one of the most active and exciting areas of modern neuroscience, with new discoveries constantly expanding our understanding of how these processes work and why they are so essential for human health and well-being. Advanced techniques like functional magnetic resonance imaging, electroencephalography, and single-cell recordings have allowed scientists to peer into the sleeping brain with unprecedented detail, revealing the intricate choreography of neural activity that unfolds each night. These research advances have practical implications for how we think about sleep and health. Understanding the importance of sleep for memory consolidation has highlighted the crucial role of adequate sleep in education and learning. Recognition of sleep's role in emotional processing has informed treatments for mood disorders and trauma. Awareness of the brain's waste clearance functions during sleep has provided new insights into neurodegenerative diseases and aging. The optimization of sleep has become an important focus for maintaining cognitive performance and overall health. Creating environments that support natural sleep rhythms, maintaining consistent sleep schedules, and addressing sleep disorders are now recognized as crucial components of preventive medicine. The simple act of prioritizing sleep has profound effects on virtually every aspect of human functioning. As you rest peacefully tonight, completely unaware of the intricate processes unfolding within your mind, your brain continues its ancient and essential work. Millions of neurons coordinate their activity with precision that exceeds the most sophisticated human technologies. Chemical messengers carry information between brain regions with timing measured in milliseconds. Waves of electrical activity sweep across your cortex with the regularity of ocean tides, each one serving specific functions in the grand orchestra of sleep. Your memories are being sorted, strengthened, and integrated with wisdom accumulated over a lifetime of experiences. Your emotions are being processed and regulated, helping you to maintain psychological balance in an often challenging world. Your brain tissue is being cleansed and maintained, protecting the neural circuits that define who you are and how you think. Your creativity is being unleashed, exploring new combinations of ideas that may lead to tomorrow's insights and innovations. All of this happens in the quiet sanctuary of sleep, hidden from conscious awareness, but absolutely essential for human life and consciousness. It is a process so fundamental that every animal species engages in some form of sleep or rest, suggesting that these functions are among the most basic requirements of complex nervous systems. Yet it is also a process so sophisticated that scientists are still discovering new aspects of how it works and why it evolved. In the gentle rhythm of your breathing, in the slow waves that traverse your sleeping brain, in the careful orchestration of hormones and neurotransmitters that guide you through the night, there lies a profound testament to the elegance and wisdom of biological evolution. Your sleeping brain represents the culmination of millions of years of refinement, a system so perfectly adapted to its functions that it operates flawlessly night after night, year after year, quietly ensuring that you wake each morning refreshed, restored, and ready to engage with the infinite complexity and beauty of conscious existence. So rest peacefully, knowing that your brain is hard at work in the most gentle and caring way possible, tending to your memories like a skilled gardener tends to precious plants, cleaning and maintaining your neural pathways like a devoted caretaker maintains a cherished home, and preparing you for tomorrow's adventures with the same loving attention that has guided human sleep for countless generations. In the quiet darkness of night, your brain keeps its faithful vigil, ensuring that the miracle of human consciousness continues uninterrupted, one peaceful sleep at a time. The intricate dance of your sleeping brain continues to unfold with layers of complexity that scientists are only now beginning to fully appreciate. As your night deepens and you settle into the most restorative phases of sleep, your neural networks engage in processes that are both ancient in their evolutionary origins and remarkably sophisticated in their execution. These processes have been quietly perfecting themselves for millions of years, creating a system so refined that it can simultaneously repair, reorganize, and optimize your brain's function, while you remain completely unaware of the profound work being accomplished. Within the depths of your hippocampus, a remarkable phenomenon begins to emerge that neuroscientists have termed memory replay. But this replay is far more complex and purposeful than simple repetition. Your brain doesn't just passively review the day's events like watching a movie. Instead, it actively reconstructs experiences, examining them from different angles, connecting them with related memories, and identifying patterns that weren't apparent during your waking hours. This process involves the coordinated activity of thousands of neurons firing in precise sequences, creating a symphony of electrical activity that can be measured and observed by researchers studying the sleeping brain. The hippocampus acts as both director and performer in this nightly theatre of memory. During your waking hours, it has been busy encoding new experiences, creating temporary neural patterns that capture the essence of everything you've learned, felt, and encountered. But these patterns are fragile and vulnerable to interference. They need to be strengthened and integrated with your existing knowledge before they can become permanent parts of your mental landscape. This integration process requires the careful coordination of multiple brain regions, each contributing its specialized expertise to the overall task of memory consolidation. As slow waves continue to wash across your cortex, they create precise windows of opportunity for this integration to occur. When these waves reach their peak, cortical neurons become highly excitable and ready to receive information from the hippocampus. During these moments, the hippocampus transmits compressed versions of the day's experiences, replaying neural patterns at speeds much faster than the original events. A conversation that lasted several minutes might be replayed in just a few seconds, allowing your brain to practice and strengthen these memory traces multiple times throughout the night. But this replay process is not random or mechanical. Your sleeping brain demonstrates remarkable intelligence in selecting which memories to strengthen and which to allow to fade. Memories that were emotionally significant, that relate to your personal goals, or that connect meaningfully with your existing knowledge receive priority treatment. These important memories are replayed more frequently and with greater intensity, ensuring that they become deeply embedded in your long-term memory networks. Meanwhile, trivial details and redundant information are gradually allowed to weaken, preventing your memory systems from becoming cluttered with unnecessary data. The selection process involves complex interactions between different neurotransmitter systems that evaluate the relative importance of different memories. Dopamine, often associated with reward and motivation, plays a crucial role in marking memories that should be prioritized for consolidation. Memories associated with positive outcomes or important learning experiences receive stronger dopaminergic signals, increasing their likelihood of being preserved and strengthened during sleep. This system ensures that your brain focuses its limited resources on the information that is most likely to be useful in future situations. As these memory consolidation processes unfold, your brain also engages in a sophisticated form of creative problem solving that occurs below the threshold of conscious awareness. The reduced activity in your prefrontal cortex during sleep removes many of the logical constraints that limit creative thinking during waking hours. This allows your brain to explore novel combinations of ideas and memories, potentially leading to insights and solutions that weren't available during conscious thought. The neural networks that process different types of information become more freely connected during sleep, enabling unusual associations and creative leaps that can result in genuine breakthroughs. This creative aspect of sleep has been documented in numerous studies, where participants have solved complex problems after sleeping on them, often waking with solutions that seemed impossible the night before. The sleeping brain appears to continue working on problems in the background, exploring different approaches and testing various combinations of known information until novel solutions emerge. This process explains why many great discoveries and artistic innovations have reportedly come to their creators in dreams or upon awakening from sleep. The neural basis of this creative processing involves changes in the connectivity patterns between different brain regions during sleep. Areas that normally operate independently during waking hours become more interconnected during certain phases of sleep, allowing information to flow between them in novel ways. The temporal lobes, which store semantic memories, can communicate more freely with the frontal regions, responsible for abstract thinking, while the visual cortex can interact with areas involved in mathematical reasoning. These unusual connections create the neurological foundation for creative insights and innovative thinking. Meanwhile, in the deeper structures of your brain, the thalamus continues its vital role as a gatekeeper and coordinator of neural activity. During waking hours, the thalamus filters incoming sensory information and helps maintain conscious awareness. But during sleep, it shifts into a different mode of operation, generating the rhythmic sleep spindles that we encountered earlier. These spindles serve multiple functions, acting as both protectors of sleep and facilitators of memory consolidation. The generation of sleep spindles involves a complex circuit within the thalamus that creates bursts of electrical activity at precise intervals. These bursts travel throughout the cortex, temporarily increasing neural excitability in specific regions, while simultaneously blocking the transmission of sensory information that might otherwise wake you up. The timing of these spindles is crucial for optimal memory consolidation, as they help coordinate the flow of information between the hippocampus and cortex during the critical moments when memories are being transferred and strengthened. Individual differences in sleep spindle activity have been linked to variations in learning ability and memory performance. People who generate more sleep spindles during the night often show better memory consolidation and are more resistant to the disruptive effects of noise and other environmental disturbances during sleep. This suggests that the thalamic circuits responsible for spindle generation play a crucial role in determining sleep quality and the effectiveness of memory processing during sleep. As your night progresses through its natural cycles, the balance between different sleep stages shifts in ways that optimize different aspects of brain function. The first half of the night is dominated by deep, slow wave sleep, during which the most intensive memory consolidation and brain maintenance occur. But as morning approaches, REM sleep periods become longer and more frequent, reflecting a shift toward different types of processing that are equally important for brain health and function. This changing pattern of sleep stages throughout the night is controlled by complex interactions between multiple brain regions and neurochemical systems. The suprachiasmatic nucleus in your hypothalamus acts as a master timekeeper, coordinating sleep timing with your body's natural circadian rhythms. But the specific transitions between sleep stages are regulated by other brain areas, including the pons in the brainstem and various nuclei in the hypothalamus that respond to internal signals about the brain's current processing needs. The shift toward more REM sleep in the latter part of the night serves important functions that complement the memory consolidation work of slow-wave sleep. During REM sleep, your brain focuses more on emotional processing, creative integration, and the formation of abstract knowledge structures. The intense neural activity during this stage allows your brain to explore connections between disparate pieces of information, potentially leading to insights and understanding that weren't available during more constrained forms of thinking. The emotional processing that occurs during REM sleep involves the coordinated activity of several brain regions that specialize in different aspects of emotional experience. The amygdala, which detects and responds to emotional significance, becomes highly active during REM sleep, working to process and integrate the emotional content of memories. The anterior cingulate cortex, which is involved in emotional regulation and decision-making, helps to modulate emotional responses and extract meaning from emotional experiences. The insular cortex, which processes bodily sensations and integrates them with emotional states, contributes to the formation of emotionally coherent memories. This emotional processing serves several important functions that extend beyond simple memory storage. During REM sleep, your brain works to reduce the emotional intensity of traumatic or highly stressful experiences while preserving the important information they contain. This process can help prevent the development of persistent emotional problems and can contribute to psychological resilience in the face of life's inevitable challenges and setbacks. The reduction in emotional intensity during sleep appears to involve changes in the connectivity between emotional brain regions and areas involved in memory storage. Traumatic memories that are processed during REM sleep often become less emotionally charged while retaining their factual content, allowing people to remember important lessons from difficult experiences without being overwhelmed by the associated emotions. This natural form of emotional regulation occurs automatically during healthy sleep and represents one of the most important functions of the dreaming brain. Dreams themselves represent one of the most fascinating and mysterious aspects of REM sleep. The vivid, often bizarre experiences that characterize dreams result from the unique pattern of brain activity that occurs during this stage of sleep. With logical constraint areas of the brain operating at reduced capacity, the dreaming mind is free to explore impossible scenarios and novel combinations of experience that would be rejected by waking consciousness. The visual imagery in dreams is generated by activity in the visual cortex, even though your eyes are closed and you're receiving no external visual input. This internally generated imagery draws from stored visual memories, recombining them in creative ways that can produce completely novel visual experiences. The temporal lobes contribute narrative structure to dreams, while the limbic system provides emotional content that can make dream experiences feel intensely real and meaningful. The apparent reality of dreams reflects the fact that the same neural systems that process real experiences during waking hours are active during dream sleep. When you see something in a dream, your visual cortex is processing that information in much the same way it would process real visual input. When you feel afraid in a dream, your amygdala is responding with the same patterns of activity that would occur during real fear. This neural similarity between dreaming and waking experience helps explain why dreams can feel so convincing and why they sometimes leave lasting emotional impressions even after awakening. The content of dreams often reflects the brain's ongoing efforts to process and integrate recent experiences with existing knowledge and concerns. Dreams frequently feature elements from the day's events, mixed with older memories and persistent worries or interests. This mixing and recombining of memory elements serves important functions in helping the brain organize information and extract general principles from specific experiences. Some dreams appear to serve as a form of mental rehearsal, allowing the brain to practice responses to challenging or threatening situations in a safe environment. Dreams of being chased, falling, or facing difficult social situations may represent the brain's attempts to prepare for similar challenges in waking life. This rehearsal function of dreams may contribute to improved problem-solving abilities and better emotional regulation when facing real-world challenges. The bizarre and often illogical nature of dreams reflects the reduced activity in brain regions responsible for critical thinking and reality testing during REM sleep. The dorsolateral prefrontal cortex, which is crucial for logical reasoning and working memory during waking hours, shows decreased activity during REM sleep. This reduction in logical constraint allows the dreaming mind to accept impossible scenarios and contradictory information without questioning their validity, creating the characteristic strangeness of dream experiences. Despite their often nonsensical content, dreams serve important functions in brain health and cognitive development. People who are deprived of REM sleep show impairments in emotional regulation, creative thinking, and certain types of learning. This suggests that the dreaming process, however strange it may seem, plays crucial roles in maintaining optimal brain function and mental health. As REM periods progress throughout the night, they tend to become more intense and emotionally significant. The final REM period before awakening often produces the most vivid and memorable dreams, which may serve to integrate the night's processing work with the upcoming demands of the day. These morning dreams sometimes contain insights or solutions to problems that have been processed during sleep, providing a bridge between the internal work of the sleeping brain and the external challenges of waking life. The transition out of REM sleep and toward morning awakening involves gradual changes in the neurochemical environment of the brain. The neurotransmitters that were suppressed during REM sleep begin to increase their activity, while the acetylcholine systems that dominated REM sleep start to normalize. This neurochemical rebalancing prepares the brain for the transition back to waking consciousness and ensures that you wake feeling alert and ready for the day's activities. Throughout these cycles of sleep, your brain's waste clearance system continues its vital work of maintaining neural health. The glymphatic system, which we explored earlier, operates most efficiently during the deeper stages of non-REM sleep, but it remains active throughout the night. The flow of cerebrospinal fluid through brain tissue follows patterns that change with different sleep stages, ensuring that all brain regions receive adequate cleaning and maintenance. During REM sleep, the glymphatic system operates somewhat differently than during slow wave sleep, with changes in fluid flow patterns that reflect the altered neural activity of this stage. The high metabolic activity of REM sleep produces its own waste products that need to be cleared, and the glymphatic system adapts its function to meet these changing demands. This adaptive capability ensures that brain cleaning remains effective throughout all stages of sleep, maintaining optimal neural health regardless of the specific type of processing that is occurring. The importance of this waste clearance function becomes apparent when sleep is disrupted or insufficient. People who experience chronic sleep deprivation or sleep disorders often show signs of impaired waste clearance, including the accumulation of proteins associated with neurodegenerative diseases. The relationship between sleep quality and long-term brain health is becoming increasingly clear as research reveals the crucial role of the glymphatic system in preventing the buildup of toxic substances in neural tissue. The hormonal regulation that occurs during sleep represents another layer of the brain's nightly maintenance activities. The release of growth hormone during deep sleep doesn't just promote physical growth and repair throughout the body, it also supports crucial brain functions, including the synthesis of proteins needed for memory consolidation and synaptic plasticity. This hormone helps to strengthen the neural connections that were modified during the day's learning experiences, making them more stable and permanent. The timing of growth hormone release is precisely coordinated with the other processes of sleep, ensuring that protein synthesis occurs when it can be most effective for brain function. The largest pulses of growth hormone typically occur during the first few hours of sleep, when slow wave activity is most intense and memory consolidation is at its peak. This coordination ensures that the raw materials needed for strengthening memories are available exactly when they are needed most. Cortisol regulation during sleep serves equally important functions for brain health. The natural decline in cortisol levels during the night creates optimal conditions for memory consolidation and neural repair. Elevated cortisol can interfere with memory formation and can promote the breakdown of neural connections. So the suppression of this stress hormone during sleep is crucial for maintaining cognitive function. People with disrupted cortisol rhythms often experience problems with memory and learning, highlighting the importance of proper hormonal regulation during sleep. The coordination of these hormonal changes is controlled by the same hypothalamic circuits that regulate sleep timing and circadian rhythms. The suprachiasmatic nucleus integrates information about light and darkness with internal signals about the body's physiological state, ensuring that hormone release occurs at optimal times for brain function and overall health. This integration represents one of the most sophisticated aspects of sleep regulation, coordinating multiple physiological systems to support the brain's complex needs. Temperature regulation during sleep involves another set of precisely coordinated changes that support optimal brain function. The gradual cooling of your core body temperature as sleep progresses serves multiple functions, including the optimization of enzymatic reactions involved in memory consolidation and waste clearance. Lower temperatures reduce the metabolic stress on neurons and may help preserve the integrity of cellular structures during the intensive processing that occurs during sleep. The temperature cycle also helps coordinate the timing of different sleep stages and physiological processes. The deepest sleep typically occurs when body temperature reaches its lowest point, usually in the early morning hours. This coordination ensures that the most intensive brain maintenance activities occur under optimal thermal conditions, maximizing their effectiveness while minimizing potential cellular stress. Breathing patterns during sleep provide another example of the intricate coordination that characterizes healthy sleep. The regular, deep breathing that occurs during slow-wave sleep helps drive the oscillations in cerebrospinal fluid flow that are crucial for waste clearance. This coordination between respiratory and neural rhythms represents a fundamental aspect of sleep physiology, ensuring that basic life support functions actively contribute to brain maintenance rather than simply operating independently. The relationship between breathing and brain activity during sleep has implications for understanding sleep disorders and their effects on cognitive function. Conditions like sleep apnea, which disrupt normal breathing patterns during sleep, can interfere with the coordination between respiratory rhythms and brainwaves, potentially compromising both memory consolidation and waste clearance functions. This helps explain why sleep breathing disorders are associated with increased risks of cognitive decline and neurodegenerative diseases. As your brain continues its nightly work, moving through cycles of different activities and processes, it demonstrates a level of organization and purpose that rivals the most sophisticated human technologies. Every aspect of sleep appears to serve specific functions that are essential for brain health and optimal cognitive performance. The coordination between different systems and processes reflects millions of years of evolutionary refinement, creating mechanisms that are both robust and adaptable to changing circumstances. The plasticity of sleep itself represents one of its most remarkable features. Your brain can adjust the timing, duration, and intensity of different sleep stages based on your individual needs and recent experiences. After periods of intensive learning, your brain may increase the amount of slow-wave sleep to enhance memory consolidation. Following emotionally stressful experiences, REM sleep may become more prominent to support emotional processing and regulation. This adaptability ensures that sleep remains optimally tuned to your brain's current requirements. Age-related changes in sleep patterns reflect the brain's changing needs throughout the lifespan. Children and adolescents, whose brains are rapidly developing and acquiring new skills, spend more time in deep sleep and show different patterns of neural activity during sleep than adults. Older adults, whose brains face different challenges related to maintenance and preservation of function, show their own characteristic sleep patterns that may reflect adaptive changes in brain physiology. These age-related differences in sleep highlight the dynamic nature of brain function and the importance of sleep throughout the entire lifespan. The processes that occur during sleep continue to be essential for brain health from infancy through old age, though the specific balance of different activities may shift to meet changing physiological needs. Understanding these changes can help optimize sleep across different life stages, supporting cognitive health and well-being throughout the human lifespan. The individual differences in sleep needs and patterns also reflect the personalized nature of brain function. Some people naturally require more deep sleep to achieve optimal memory consolidation, while others may need more REM sleep for adequate emotional processing. These differences are determined by a complex interplay of genetic factors, life experiences, and current circumstances, creating unique sleep signatures that are as individual as fingerprints. Research into these individual differences is helping to develop more personalized approaches to sleep optimization and the treatment of sleep disorders. Rather than applying one-size-fits-all recommendations, healthcare providers are increasingly recognizing the importance of tailoring sleep interventions to individual needs and characteristics. This personalized approach promises to improve both the effectiveness of sleep treatments and our understanding of how sleep contributes to individual differences in cognitive ability and mental health. The study of sleep continues to reveal new insights into brain function and the maintenance of cognitive health. Advanced neuroimaging techniques allow researchers to observe the sleeping brain with unprecedented detail, revealing the intricate patterns of activity that support different aspects of sleep function. Single-cell recording studies provide insights into how individual neurons contribute to sleep processes, while large-scale population studies help identify the factors that promote healthy sleep across different groups of people. These research advances are not merely academic curiosities, but have practical implications for improving human health and performance. Understanding the mechanisms of memory consolidation during sleep is informing educational practices and learning strategies. Knowledge of emotional processing during REM sleep is contributing to new treatments for trauma and mood disorders. Insights into the brain's waste clearance functions are suggesting new approaches to preventing neurodegenerative diseases. The recognition of sleep as an active, essential process, rather than simply a passive state of rest, has transformed our understanding of brain health and human performance. Sleep is now recognized as a third pillar of health alongside diet and exercise, with its own specific requirements and benefits that cannot be replaced by other interventions. This shift in perspective has profound implications for how we structure our lives and prioritize our health. As you continue your journey through the night, your brain maintains its vigilant care of your mental faculties with the same dedication it has shown for countless generations of human ancestors. The processes unfolding within your sleeping mind represent the culmination of evolutionary wisdom, refined over millions of years, to support the complex cognitive abilities that define human consciousness. Each cycle of brain waves, each pulse of cerebrospinal fluid, each replay of neural patterns contributes to a maintenance system so sophisticated that it operates flawlessly night after night throughout your entire life. The quiet efficiency of your sleeping brain reflects a profound truth about the nature of consciousness and cognition. The brilliant complexity of human thought, the rich tapestry of memory and emotion that defines your inner life, the creative insights that drive innovation and discovery all depend on the humble, invisible work that occurs during sleep. In the gentle rhythm of neural oscillations and the careful choreography of neurochemical changes, your brain tends to the garden of consciousness with infinite patience and skill. This nightly renewal process ensures that you wake each morning not merely rested, but genuinely restored. with your cognitive faculties refreshed and optimized for the challenges and opportunities of a new day. Your memories are more stable, your emotions are better regulated, your creative faculties are enhanced, and your brain tissue is clean and healthy. All of this occurs automatically, guided by biological wisdom that operates below the threshold of consciousness, yet supports everything that consciousness makes possible. The marvel of sleep lies not only in its complexity, but in its accessibility. This sophisticated neural maintenance system requires no conscious effort, no special training, no expensive equipment or interventions. It asks only that you provide the time and conditions for it to unfold naturally, trusting in the ancient wisdom of your own biology to accomplish what no external intervention could achieve. In surrendering to sleep, you participate in one of life's most fundamental and essential processes, one that connects you to every living creature that has ever existed. So as you rest peacefully in the embrace of sleep, know that your brain is engaged in its most important work, quietly ensuring that the miracle of human consciousness continues unimpaired and enhanced. In the gentle waves that traverse your sleeping mind, in the careful sorting and strengthening of memories, in the cleansing flows that wash through neural pathways, your brain demonstrates a love and care for your well-being that surpasses understanding. This nightly gift of restoration and renewal happens without fanfare or recognition, yet it makes possible everything else that life has to offer. Rest well, knowing that in sleep you are participating in one of nature's most beautiful and essential processes, one that has been perfected over eons of evolution to serve the magnificent complexity of the human mind. Your sleeping brain keeps its faithful watch through the quiet hours, ensuring that when morning comes, you will wake refreshed, restored, and ready to engage once more with the infinite wonder of conscious existence. The quiet symphony of your sleeping brain continues through the night, each moment bringing new layers of restoration and renewal that unfold with the gentle precision of nature's most refined processes. As you drift deeper into the embrace of sleep, your neural networks begin to engage in activities that are both profoundly complex and beautifully simple in their purpose. These processes have been quietly perfecting themselves for countless generations, creating a system so elegant that it operates with the same faithful reliability as the tides or the turning of seasons. In the deeper recesses of your brain, within the intricate folds of the hippocampus, something truly remarkable begins to take shape. This seahorse-shaped structure, no larger than your thumb, becomes the conductor of an elaborate neural orchestra that will play throughout the night. The hippocampus has spent your waking hours carefully collecting and temporarily storing the countless experiences that made up your day. Every conversation, every new sight, every moment of learning has left its mark in the form of delicate neural patterns that shimmer like morning dew across the landscape of your mind. But these temporary impressions cannot remain in the hippocampus indefinitely. Like a library with limited shelf space, this remarkable structure must carefully curate its collection, deciding which memories deserve permanent preservation and which can be gently allowed to fade. This process of selection and transfer represents one of the most sophisticated information management systems in the known universe, operating with a wisdom that has been refined through millions of years of evolutionary development. As slow waves continue to wash across your cortex in their gentle rhythmic patterns, they create perfect conditions for this delicate work of memory curation. Each wave acts like a messenger, carrying carefully encoded information from the temporary storage of the hippocampus to the vast library of your cortical regions. These waves move with the unhurried pace of ocean swells, taking their time to ensure that each precious memory is handled with the care it deserves. The process unfolds like a careful dance between different regions of your brain. The hippocampus begins to replay the neural patterns that were active during your most meaningful experiences, but these replays occur in a compressed, accelerated format that allows your brain to review hours of experience in just minutes. It's as if your mind is creating a highlight reel of your day, focusing on the moments that were most significant, most emotional, or most likely to be useful in future situations. This replay process is not random or mechanical, but demonstrates a remarkable intelligence in its selection criteria. Memories that were accompanied by strong emotions receive special attention, as your brain recognizes that emotionally significant events are often the most important to remember. Experiences that connected with your existing knowledge or personal interests are also prioritized, as these memories are more likely to be useful in helping you navigate similar situations in the future. Meanwhile, routine details and redundant information are gradually allowed to weaken, freeing up neural resources for more important memories. The transfer of memories from hippocampus to cortex happens gradually over many nights of sleep. Each time a memory is replayed and transmitted, the neural pathways that support it become a little stronger, a little more stable. Over weeks and months, these repeated transmissions transform fragile temporary memories into robust, permanent parts of your knowledge base. This gradual process ensures that your most important memories become deeply embedded in your brain's architecture, resistant to forgetting and readily available when you need them. But memory consolidation involves more than simply moving information from one brain region to another. As memories are transferred and strengthened, your brain also begins to extract the deeper patterns and principles that underlie your experiences. Rather than just remembering specific facts or events, your sleeping brain works to understand the relationships between different pieces of information, creating flexible knowledge structures that can be applied in novel situations. This process of abstraction and generalization allows your brain to transform raw experience into genuine wisdom. For example, rather than just remembering individual instances of social interaction, your brain extracts general principles about human behavior that can guide your actions in future social situations. Instead of merely storing facts about specific places you visited, your brain develops spatial and navigational knowledge that can help you find your way in unfamiliar environments. The neural mechanisms that support this abstraction process involve complex interactions between the hippocampus and various regions of the cortex that specialize in different types of knowledge. The temporal lobes, which store semantic information about concepts and categories, work with the hippocampus to identify common features across different experiences. The parietal cortex, which processes spatial and quantitative information, helps extract mathematical and spatial relationships from stored memories. The frontal regions, which support abstract thinking and planning, contribute to the formation of general principles and rules. As these different cortical regions collaborate with the hippocampus during sleep, they create increasingly sophisticated representations of your knowledge and experience. These representations are not static storage files, but dynamic, interconnected networks that can be activated and recombined in creative ways. This flexibility is what allows you to apply old knowledge to new situations, to see connections between seemingly unrelated ideas, and to generate creative solutions to novel problems. The coordination of this memory processing work requires exquisite timing that is orchestrated by the natural rhythms of your sleeping brain. The slow waves that characterize deep sleep create periodic windows of opportunity during which different brain regions can communicate effectively. When these waves reach their peak, cortical neurons become highly responsive to input from the hippocampus, allowing memory information to be transmitted efficiently. During the troughs between waves, cortical activity quiets down, allowing the newly received information to stabilize and integrate with existing memory networks. Nested within these slow waves are the sleep spindles we encountered earlier, those brief bursts of rhythmic activity generated by the thalamus. These spindles serve as precise timing signals that help coordinate the flow of information between brain regions. When spindles occur at just the right moment in relation to slow waves, the efficiency of memory consolidation increases dramatically. This temporal coordination represents one of the most elegant examples of neural timing in the entire nervous system, demonstrating how your brain uses rhythm and synchronization to optimize its most important functions. The generation of sleep spindles involves a complex circuit within the thalamus that operates like a biological metronome. creating regular pulses of activity that help keep different brain regions synchronized. The neurons responsible for generating these spindles are exquisitely sensitive to the overall state of your brain, adjusting their timing and intensity based on your current sleep depth and the specific memory processing needs of the moment. This adaptive capability ensures that spindles provide optimal support for memory consolidation throughout the night. Individual differences in sleep spindle activity help explain why some people are naturally better at learning and remembering new information. Research has shown that people who generate more sleep spindles during the night often show superior memory consolidation and are better able to integrate new information with their existing knowledge. These individual differences appear to be partly genetic and partly influenced by factors like age, health, and sleep quality, highlighting the personalized nature of brain function and the importance of optimizing sleep for individual needs. As your brain continues its work of memory consolidation, it simultaneously engages in another crucial process that scientists have only recently begun to understand: the active forgetting of information that is no longer needed. This forgetting process is not a failure of memory, but rather a sophisticated form of cognitive housekeeping that helps keep your mind organized and efficient. Just as a well-maintained garden requires both planting and weeding, optimal brain function requires both remembering important information and forgetting irrelevant details. The mechanisms of active forgetting involve many of the same neural systems that participate in memory consolidation, but they operate in the opposite direction. Instead of strengthening synaptic connections between neurons, these systems selectively weaken connections that support memories targeted for forgetting. This process requires energy and effort, demonstrating that forgetting is an active, intentional function rather than passive decay. The selection of memories for forgetting follows intelligent criteria that help optimize your cognitive resources. Memories that are no longer relevant to your current goals or circumstances are prime candidates for forgetting. Details that were important at one time but have since been superseded by more recent information are gradually allowed to fade. Redundant information that duplicates knowledge stored elsewhere in your brain is also subject to selective forgetting, freeing up neural resources for new learning. This process of selective forgetting serves several important functions beyond simply managing storage capacity. It reduces interference between similar memories, making it easier to retrieve the specific information you need in any given situation. It helps extract general principles from specific experiences by allowing unique details to fade while preserving common features. And it contributes to emotional healing by gradually reducing the intensity of painful memories while preserving the important lessons they contain. The coordination between remembering and forgetting during sleep creates a dynamic balance that keeps your memory systems optimally tuned. Too much consolidation without sufficient forgetting would lead to cluttered, inefficient memory networks filled with outdated and irrelevant information. Too much forgetting without adequate consolidation would result in the loss of important knowledge and experiences. The precise balance achieved during healthy sleep ensures that your memory remains both comprehensive and efficient, storing what you need while discarding what you don't. As the night progresses and your brain cycles through its natural rhythms, the focus of neural activity begins to shift toward different types of processing that are equally important for cognitive health. The intense memory consolidation work of early sleep gives way to other forms of neural maintenance that will prepare your mind for optimal function in the coming day. These transitions occur gradually and smoothly, guided by internal biological rhythms that have been precisely calibrated over evolutionary time. The shift toward lighter stages of sleep brings changes in brainwave patterns that reflect different processing priorities. The large, synchronized delta waves of deep sleep give way to faster, more complex patterns that include bursts of theta and alpha activity. These faster rhythms create conditions that are optimal for different types of neural processing, including the integration of emotional memories and the formation of creative associations between disparate pieces of information. During these transitional periods, your brain begins to focus more intensively on emotional processing and regulation. The limbic system, which includes structures like the amygdala, hippocampus, and cingulate cortex, becomes increasingly active as sleep progresses toward morning. This increased limbic activity reflects your brain's efforts to process and integrate the emotional content of your memories, helping to maintain psychological balance and emotional resilience. The emotional processing that occurs during sleep serves functions that are crucial for mental health and well-being. Memories that were formed during emotionally intense experiences are revisited and processed in ways that help reduce their emotional impact while preserving their informational content. This natural form of emotional regulation can help prevent the development of persistent anxiety, depression, or post-traumatic stress responses to difficult life experiences. The neural mechanisms of emotional processing during sleep involve complex interactions between different components of the limbic system. The amygdala, which initially responds to emotional significance with alarm and arousal, gradually reduces its reactivity as memories are processed during sleep. The hippocampus helps contextualize emotional memories, placing them within a broader framework of understanding that reduces their threat value. The prefrontal cortex, even though it operates at reduced capacity during sleep, still contributes to emotional regulation by helping to reframe experiences in more adaptive ways. This emotional processing work is particularly important for memories that involve social interactions, personal challenges, or threatening situations. During sleep, your brain works to extract the useful information from these experiences while reducing their capacity to trigger ongoing stress or anxiety. A difficult conversation with a colleague might be processed in ways that preserve the important lessons about communication while reducing the emotional sting of criticism. A challenging situation at work might be reframed as a learning opportunity rather than a source of ongoing worry. The gradual reduction in emotional intensity that occurs during sleep processing helps explain why people often feel better about upsetting events after sleeping on them. This common wisdom reflects a real neurobiological process that helps maintain emotional equilibrium in the face of life's inevitable challenges and setbacks. The sleeping brain essentially provides a form of natural therapy, helping to process difficult experiences in ways that promote psychological healing and growth. As your brain continues its emotional processing work, it also begins to engage in more creative and integrative forms of thinking that can lead to genuine insights and innovations. The reduced activity in logical constraint areas of the brain during sleep allows for more flexible and associative thinking patterns that can generate novel solutions to problems and new perspectives on familiar challenges. This creative aspect of sleep processing involves changes in the connectivity patterns between different brain networks. During waking hours, different cognitive systems tend to operate relatively independently, with clear boundaries between areas responsible for different types of thinking. But during sleep, these boundaries become more permeable, allowing information to flow between systems in novel ways that can generate unexpected insights. The default mode network, which is active during rest and introspection, becomes particularly important during these creative processing periods. This network includes brain regions involved in self-referential thinking, memory retrieval, and imagining future scenarios. During sleep, the default mode network can operate with greater freedom, exploring unusual combinations of memories and generating novel associations that might not occur during more constrained waking thought. The creative insights that emerge from sleep processing often involve the recognition of previously hidden patterns or relationships between different pieces of information. A scientist might wake with a solution to a research problem that had seemed intractable the night before. An artist might discover a new creative direction that synthesizes influences from seemingly unrelated sources. A business person might see a novel approach to a challenging situation that combines insights from different areas of experience. These creative breakthroughs reflect the brain's remarkable ability to continue working on problems in the background during sleep, exploring different approaches and testing various combinations of known information until novel solutions emerge. This process occurs below the threshold of conscious awareness, which may actually enhance its effectiveness by removing the self-doubt and premature criticism that can interfere with creative thinking during waking hours. The neural basis of creative insight during sleep involves the temporary reorganization of brain networks in ways that promote unusual connections and associations. Brain regions that normally operate independently can communicate more freely during certain phases of sleep, allowing information stored in different areas to be combined in novel ways. The visual cortex might interact with areas involved in mathematical reasoning, leading to insights about spatial relationships. The language centers might connect with emotional processing regions, generating new forms of artistic expression. This temporary reorganization of brain connectivity during sleep may help explain why many great discoveries in creative works have reportedly emerged from dream experiences or upon awakening from sleep. The sleeping brain appears to be particularly adept at seeing connections that are invisible to waking consciousness, exploring possibilities that would be rejected by logical analysis, and generating solutions that transcend conventional thinking patterns. The integration of creative processing with memory consolidation and emotional regulation during sleep creates a comprehensive system for cognitive optimization that addresses multiple aspects of mental function simultaneously. While your brain strengthens important memories, it also explores creative applications of that knowledge. While it processes emotional experiences, it also searches for innovative ways to understand and respond to challenging situations. This multi-layered approach to cognitive maintenance ensures that you wake not only with better organized memories and more stable emotions, but also with enhanced creative potential. As the night continues to unfold, your brain begins to prepare for the transition toward REM sleep, the stage that will bring some of the most intense and fascinating neural activity of the entire sleep cycle. This preparation involves gradual changes in neurotransmitter activity and brainwave patterns that create the unique neurochemical environment necessary for the vivid dreaming experiences that characterize REM sleep. The transition into REM sleep is marked by dramatic changes in the activity of different neurotransmitter systems that control various aspects of consciousness and cognition. The neurons that normally release norepinephrine, serotonin, and histamine, chemicals that promote alertness and logical thinking during waking hours, begin to reduce their activity significantly. At the same time, neurons that release acetylcholine, a neurotransmitter associated with attention and memory processing, become increasingly active. This unique neurochemical profile creates conditions that are unlike any other state of consciousness. The reduced activity of alertness-promoting neurotransmitters allows consciousness to become more fluid and less constrained by logical rules. The increased acetylcholine activity enhances the vividness and emotional intensity of mental experiences. Together, these changes create the neurochemical foundation for the rich, often bizarre world of dreams that will unfold during REM sleep. The preparation for REM sleep also involves changes in brainwave patterns that reflect the transition toward this unique form of consciousness. The slow, synchronized waves that characterize deep sleep begin to give way to faster, more complex patterns that resemble those seen during waking consciousness. These faster rhythms, dominated by theta waves oscillating at 4 to 8 cycles per second, create the neural substrate for the vivid imagery and narrative complexity of dreams. The emergence of theta rhythms during the transition to REM sleep reflects increased activity in brain regions involved in memory retrieval, emotional processing, and sensory imagination. The hippocampus, which has been focused on memory consolidation during earlier sleep stages, begins to shift toward a more creative and integrative mode of processing. The visual cortex, despite receiving no external visual input, begins to generate the rich imagery that will characterize dream experiences. The temporal lobes, which process language and narrative, prepare to contribute to the story-like quality of dreams. As these preparatory changes unfold, your brain also implements one of the most remarkable protective mechanisms in all of physiology, the temporary paralysis that will prevent you from acting out your dreams. This paralysis is controlled by specialized neurons in the brainstem that actively inhibit the motor neurons responsible for voluntary movement. The inhibition is so complete that even the most intense dream actions result in only minimal muscle twitches. This protective paralysis serves crucial functions for both your safety and the quality of your sleep. Without it, the vivid experiences of dreams could lead to dangerous physical actions that might cause injury to yourself or others. The paralysis also helps maintain the internal focus necessary for optimal dream processing by preventing external movement from disrupting the delicate neural processes that generate and sustain dream consciousness. The mechanisms that control REM paralysis involve complex circuits within the brainstem that must precisely coordinate the timing and extent of muscle inhibition. These circuits must allow continued function of essential muscles involved in breathing and circulation while completely blocking voluntary movement. The precision required for this selective paralysis represents one of the most sophisticated examples of neural control in the entire nervous system. Occasionally, the systems that control REM paralysis may not function perfectly, leading to sleep disorders in which people act out their dreams physically. These conditions highlight the importance of the paralysis mechanism and demonstrate how crucial it is for safe, restorative sleep. The study of such disorders has provided valuable insights into the neural circuits that control movement during sleep and has contributed to our understanding of how the brain maintains the proper balance between dream consciousness and physical safety. As your brain completes its preparation for REM sleep, all of these systems coordinate to create the unique state of consciousness that will dominate the final hours of your night. The neurochemical changes, the altered brainwave patterns, the protective paralysis, and the increased activity in memory and emotional processing regions all work together to create optimal conditions for the remarkable experiences that await in the world of dreams. The transition into full REM sleep brings a dramatic transformation in the landscape of consciousness that rivals any science fiction vision of altered states of mind. Your brain activity increases to levels that match or even exceed those seen during waking consciousness. Yet you remain deeply asleep and largely disconnected from the external world. This paradox of high activity combined with unconsciousness creates the unique state that researchers call paradoxical sleep. The neural activity during a REM sleep is dominated by the interplay between different brain regions that normally operate with more independence during waking hours. The visual cortex becomes remarkably active, generating the rich, detailed imagery that characterizes most dreams. This activity occurs despite the fact that your eyes are closed and you're receiving no visual input from the environment. The images in dreams are created entirely by your brain's own activity, drawing from stored visual memories and recombining them in ways that can seem incredibly real and immediate. The temporal lobes, which process language and construct narratives, contribute to the story-like quality that gives dreams their characteristic flow from scene to scene. Even the most bizarre dream experiences typically unfold with a narrative structure that includes characters, settings, and sequences of events. This narrative quality reflects the brain's fundamental tendency to organize experience into meaningful stories, a tendency that continues even in the altered state of dream consciousness. The limbic system, which processes emotions and motivation, becomes highly active during REM sleep. imbuing dream experiences with intense feelings that can range from joy and wonder to fear and anxiety. The emotional intensity of dreams often exceeds that of waking experiences, as the neural circuits that normally regulate emotional responses operate with less constraint during sleep. This emotional richness contributes to the memorable quality of many dreams and may serve important functions in emotional processing and regulation. The prefrontal cortex, which is responsible for logical thinking, reality testing, and executive control during waking hours, shows significantly reduced activity during REM sleep. This reduction in logical constraint allows the dreaming mind to accept impossible scenarios, contradictory information, and bizarre transformations without questioning their validity. The result is a form of consciousness that is freed from the logical rules that normally govern thinking, creating space for novel associations and creative insights to emerge. This unique pattern of brain activity during REM sleep creates the neurological foundation for the remarkable experiences we call dreams. Dreams can transport you to impossible places, allow you to interact with people from your past, and create scenarios that blend memory, imagination, and emotion in ways that feel intensely real, despite their often illogical content. The vividness and apparent reality of dreams reflects the fact that many of the same neural systems that process real experiences during waking hours are active during dream sleep. When you see something in a dream, your visual cortex is processing that information using the same neural pathways it would use to process real visual input. When you feel afraid in a dream, your amygdala is responding with patterns of activity that closely resemble those that occur during real fear. When you hear sounds or voices in dreams, your auditory cortex is generating those experiences using the same mechanisms it uses to process real sounds. This neural similarity between dreaming and waking experience helps explain why dreams can feel so convincing and why they sometimes leave lasting emotional impressions. The content of dreams reflects the brain's ongoing efforts to process and integrate recent experiences with existing memories and concerns. Dreams frequently feature elements from the day's events, but these elements are typically mixed and recombined with older memories in ways that create new scenarios and narratives. A conversation with a colleague might blend with childhood memories and future concerns to create a dream scenario that addresses multiple themes simultaneously. This mixing and recombining of memory elements serves important functions in helping the brain organize information and extract general principles from specific experiences. By exploring different combinations of stored information, dreams may help identify patterns and relationships that weren't apparent during waking thought. The unusual associations that characterize dream content may contribute to creative problem solving and innovative thinking by allowing the mind to explore possibilities that would be rejected by logical analysis. Some dreams appear to serve as a form of mental rehearsal, allowing the brain to practice responses to challenging or threatening situations in a safe psychological environment. Dreams of being chased, falling, facing difficult social situations, or dealing with various forms of conflict may represent the brain's attempts to prepare for similar challenges in waking life. This rehearsal function may contribute to improved coping skills and better emotional regulation when facing real-world stresses. The bizarre and often impossible nature of dreams reflects the unique neurochemical environment of REM sleep, in which logical constraint is minimized and creative association is maximized. The reduced activity in brain regions responsible for reality testing allows the dreaming mind to accept contradictory information, impossible transformations, and illogical sequences without question. This creates a form of consciousness that is uniquely suited for exploring novel possibilities and generating creative insights. Despite their often nonsensical content, dreams serve important functions in brain health and cognitive development that are only now being fully appreciated by neuroscientists. People who are deprived of REM sleep show impairments in emotional regulation, creative thinking, and certain types of learning and memory. This suggests that the dreaming process, however strange it may seem, plays crucial roles in maintaining optimal brain function and mental health. The emotional processing that occurs during REM sleep appears to be particularly important for psychological well-being. Dreams often feature intense emotional content that may help the brain work through unresolved feelings and conflicts from waking life. The high activity in emotional brain regions during REM sleep, combined with the reduced influence of logical constraint, creates optimal conditions for processing difficult emotions and traumatic experiences in ways that promote healing and integration. Research has shown that people who experience adequate REM sleep show better emotional regulation and resilience in the face of stress and adversity. The emotional processing that occurs during dreams may help reduce the psychological impact of difficult experiences while preserving the important lessons they contain. This natural form of emotional regulation occurs automatically during healthy sleep and represents one of the most important functions of the dreaming brain. The creative insights that can emerge from dream experiences reflect the brain's remarkable ability to generate novel solutions and perspectives when freed from the constraints of logical thinking. Many scientific discoveries, artistic innovations, and technological breakthroughs have reportedly emerged from dream experiences or from the relaxed associative thinking that characterizes the transition between sleep and waking. The dreaming brain's ability to see connections that are invisible to waking consciousness may contribute significantly to human creativity and problem-solving ability. As REM periods progress throughout the night, they tend to become longer and more intense, with the most vivid and emotionally significant dreams typically occurring in the early morning hours. This pattern reflects the natural rhythm of neurotransmitter activity and ensures that the important functions of REM sleep are completed before awakening. The increasing intensity of late-night REM sleep may also serve to prepare the brain for the transition back to waking consciousness. The final REM period before awakening often produces dreams that seem to integrate the night's processing work with concerns about the coming day. These morning dreams may contain insights or solutions to problems that have been processed during sleep, providing a bridge between the internal work of the sleeping brain and the external challenges of waking life. The timing of these dreams ensures that any insights or emotional resolutions achieved during sleep are fresh in memory as consciousness returns. Throughout the cycles of REM sleep, your brain maintains its essential life support functions while engaging in the complex processing that characterizes this remarkable state of consciousness. Breathing continues, though it becomes more irregular and variable than during other sleep stages. Heart rate and blood pressure fluctuate in response to dream content, sometimes matching the emotional intensity of dream experiences. Body temperature regulation is temporarily suspended, making you more sensitive to environmental temperature during REM sleep. These physiological changes reflect the brain's focus on internal processing rather than external regulation during REM sleep. The temporary reduction in temperature control and the irregularity in breathing and heart rate demonstrate how profoundly different this state is from both waking consciousness and other stages of sleep. Yet these changes occur within safe parameters that protect your health while allowing optimal conditions for the important psychological processing that characterizes REM sleep. The coordination of all these physiological and psychological processes during REM sleep represents one of the most sophisticated examples of biological regulation in the natural world. Your brain must simultaneously maintain essential life functions, generate complex conscious experiences, process emotions and memories, and prepare for eventual awakening, all while keeping you safely asleep and protected from external disturbances. The precision and reliability with which this coordination occurs night after night throughout your lifetime represents a remarkable achievement of evolutionary development. As your REM periods draw to a close and morning approaches, your brain begins the gradual process of preparing for the return to waking consciousness. This preparation involves subtle changes in neurotransmitter activity, brainwave patterns, and hormonal regulation that will gently guide you back toward the waking world. This transition is not abrupt, but unfolds with the same careful precision that has characterized your entire night's journey through sleep. The neurochemical systems that have been orchestrating your dreams begin to shift their balance, gradually restoring the conditions necessary for alert, focused consciousness. The neurons that release norepinephrine, serotonin, and histamine, which remained largely quiet during REM sleep, begin to increase their activity in gentle waves. These neurotransmitters, essential for maintaining attention and logical thinking during waking hours, return to your neural circuits like morning sunlight gradually illuminating a darkened room. The process occurs slowly and smoothly, ensuring that the transition from dream consciousness to waking awareness feels natural and comfortable rather than jarring or disorienting. At the same time, the acetylcholine systems that dominated your dream experiences begin to normalize their activity patterns, shifting from the intense, focused release that characterized REM sleep to the more balanced pattern that supports alert wakefulness. This neurochemical rebalancing happens gradually over the course of your final sleep cycles, preparing your brain for the complex demands of conscious thought and interaction with the external world. Your body temperature, which reached its lowest point during the deepest phases of sleep, begins to rise as morning approaches. This warming process is controlled by your hypothalamus, that master regulator of biological rhythms, which responds to both internal circadian signals and subtle environmental cues that herald the approaching dawn. The gentle increase in core temperature helps activate metabolic processes throughout your body and brain, preparing every cell for the energy demands of the coming day. The hormonal symphony that has been playing throughout your night also begins to shift toward its daytime composition. Cortisol, which remained low during the night to create optimal conditions for memory consolidation and neural repair, begins to increase in carefully timed pulses. This morning rise in cortisol is not a stress response, but rather a natural awakening signal that helps mobilize your body's resources and prepare you for the activities ahead. The timing of this cortisol increase is precisely coordinated with your circadian rhythms, ensuring that you wake feeling alert and energized, rather than groggy or disoriented. Growth hormone, which surged during your deepest sleep to support memory consolidation and tissue repair, begins to return to its lower daytime levels. The work of this remarkable hormone is largely complete by morning, having spent the night facilitating the protein synthesis necessary for strengthening neural connections and repairing cellular damage accumulated during your previous day of activity. The gradual decline in growth hormone signals that the intensive maintenance work of sleep is drawing to a close. Melatonin, that gentle chemical messenger that helped guide you into sleep many hours ago, begins its own gradual retreat as morning light starts to influence your brain's master clock. Even before you open your eyes, specialized cells in your retina begin to detect the increasing brightness of dawn, sending signals to your suprachiasmatic nucleus that it's time to suppress melatonin production and prepare for wakefulness. This light-sensitive system ensures that your sleep-wake cycle remains synchronized with the natural rhythm of day and night. As these neurochemical and hormonal changes unfold, your brainwaves undergo their own gentle transformation. The theta rhythms that characterized your REM sleep begin to give way to the alpha waves that mark relaxed wakefulness. These alpha waves, oscillating at 8 to 12 cycles per second, represent a bridge between the internal focus of sleep and the external awareness of waking consciousness. They create a state of calm alertness that allows you to transition smoothly from the dream world to the demands of daily life. The emergence of alpha waves reflects increasing activity in brain regions that will soon need to engage with the external world. Your thalamus, which has been filtering sensory information throughout the night, begins to open its gates more widely, allowing the sights and sounds of your environment to reach your conscious awareness with increasing clarity. Your prefrontal cortex, which operated at reduced capacity during sleep, starts to reactivate its executive functions, preparing to take control of your thoughts, decisions, and actions. Your motor cortex gradually regains control over voluntary movement as the protective paralysis of REM sleep slowly lifts. This return of motor control happens gradually and smoothly, allowing you to stretch and move naturally as consciousness returns. The precise timing of this process ensures that you regain full control of your body just as your mind becomes ready to direct purposeful action. The visual cortex, which spent the night generating the rich imagery of dreams, begins to prepare for processing real visual input from your eyes. The auditory cortex shifts from creating the sounds and voices of dreams to receiving and interpreting actual sounds from your environment. All of your sensory processing systems undergo this gentle transition from internal generation to external reception, preparing you to fully engage with the world around you. As morning consciousness gradually returns, you may become aware of lingering dream images or emotions from your final REM period. These dream fragments represent the last products of your brain's nighttime processing, often containing insights or resolutions that emerge during sleep. The fact that morning dreams are often the most memorable reflects their timing near the transition to wakefulness, when your brain is beginning to form the kinds of stable memories that characterize conscious experience. The content of these morning dreams may feel particularly relevant or meaningful because they often represent a synthesis of the night's processing work. Your sleeping brain has spent hours organizing memories, processing emotions, and exploring creative connections between different pieces of information. The dreams that occur just before awakening may reflect the culmination of this work, presenting insights or perspectives that weren't available to your conscious mind the night before. The gradual return of consciousness brings with it a renewed sense of mental clarity and emotional balance that reflects the restorative work your brain has accomplished during sleep. The memories that were consolidated during the night now feel more stable and accessible. The emotional experiences that were processed during REM sleep feel less overwhelming and more manageable. The creative connections that were explored during dreams may manifest as new ideas or solutions to problems that seemed intractable before sleep. This morning renewal is not simply the result of physical rest, but reflects the sophisticated cognitive maintenance that occurs during sleep. Your brain has spent the night cleaning house, organizing information, and optimizing its function for the challenges ahead. The neural pathways that support learning and memory have been strengthened and refined. The emotional circuits that regulate your responses to stress and challenge have been recalibrated and balanced. The waste clearance system that operated throughout your sleep has left your brain tissue clean and healthy, free from the metabolic toxins that accumulated during your previous day of activity. The glymphatic system, that remarkable cleaning network, has flushed away proteins and cellular debris that could otherwise impair cognitive function over time. This nightly cleaning process is so thorough and efficient that it maintains optimal brain health year after year, protecting the neural circuits that define your thoughts, memories, and personality. As you become fully awake, your breathing pattern shifts from the controlled rhythms of sleep to the more variable patterns of waking consciousness. Your heart rate increases slightly as your cardiovascular system prepares to support the activities of the day. Your muscles regain their full tone and responsiveness, ready to carry you through whatever physical demands await. Every system in your body has been restored and optimized during your night of sleep, preparing you for optimal performance in the hours ahead. The transition from sleep to wakefulness represents one of the most remarkable transformations in human physiology. Yet it occurs so smoothly and naturally that you typically take it for granted. In just a few minutes, your brain shifts from the inward-focused, maintenance-oriented activity of sleep to the outward-directed, goal-oriented activity of waking consciousness. This transformation involves the coordinated activity of millions of neurons, the precise timing of multiple neurotransmitter systems, and the careful orchestration of countless physiological processes. The fact that this transition occurs reliably every morning throughout your entire lifetime represents a testament to the robustness and precision of the biological systems that control sleep and wakefulness. These systems have been refined through millions of years of evolution, creating mechanisms that are both incredibly sophisticated and remarkably reliable. They operate automatically, without requiring any conscious effort or control, yet they adapt flexibly to changing circumstances and individual needs. The benefits of your night's sleep extend far beyond the simple feeling of being rested. Your cognitive abilities have been enhanced through memory consolidation and neural optimization. Your emotional resilience has been strengthened through the processing and regulation that occurred during REM sleep. Your creativity has been unleashed through the novel associations and insights generated during dreams. Your physical health has been supported through hormonal regulation and cellular repair processes. Perhaps most importantly, your brain's capacity for learning and adaptation has been restored and optimized for the challenges ahead. The neural plasticity that allows you to acquire new skills, adapt to changing circumstances, and continue growing throughout your lifetime has been enhanced by the restorative processes of sleep. You wake not just rested, but renewed, with your mind prepared for whatever learning opportunities and challenges the day may bring. The sleep you have just completed represents far more than a period of rest and recovery. It has been a time of active maintenance, creative processing, and careful optimization of your brain's most important functions. Every aspect of your cognitive abilities, from basic attention and memory to complex reasoning and emotional regulation, has benefited from the sophisticated processes that unfolded while you slept peacefully and unaware. As you move into your day, carrying with you the benefits of your brain's nighttime work, you participate in one of the most fundamental rhythms of life on Earth. The cycle of sleep and wakefulness that governs your daily experience connects you to every living creature that has ever existed, from the smallest insects to the largest mammals. This ancient rhythm has shaped the evolution of consciousness itself, creating the conditions necessary for complex thought, rich emotional experience, and the remarkable creativity that defines human existence. The sleep you have experienced represents the culmination of millions of years of evolutionary refinement, a process so elegant and essential that it continues to operate with perfect reliability throughout your entire lifetime. Night after night, year after year, your brain engages in this sophisticated maintenance routine, quietly ensuring that the miracle of human consciousness continues unimpaired and enhanced. The processes that unfolded while you slept represent some of the most complex and beautiful phenomena in all of biology, yet they occur so naturally and effortlessly that they rarely receive the recognition they deserve. In the gentle rhythm of neural oscillations that swept across your sleeping brain, in the careful sorting and strengthening of memories that occurred throughout the night, in the cleansing flows that washed through your neural pathways, your brain demonstrated a form of care and attention that surpasses conscious understanding. This nightly gift of restoration and renewal happens without fanfare or recognition, yet it makes possible everything else that consciousness has to offer. The work your brain accomplished during sleep reflects a profound wisdom that has been encoded in your biological systems through countless generations of evolutionary development. This wisdom operates below the threshold of conscious awareness, yet it guides and supports every aspect of your mental life. It ensures that you wake each morning not merely rested, but genuinely restored, with your cognitive faculties refreshed and optimized for the infinite complexity and beauty of conscious existence. As you begin this new day, carry with you an appreciation for the remarkable processes that have prepared you for whatever lies ahead. Your sleeping brain has tended to your memories like a careful gardener tends to precious plants, organizing and nurturing them so they can continue to grow and flourish. It has cleaned and maintained your neural pathways like a devoted caretaker maintains a cherished home, ensuring that everything functions optimally for the challenges ahead. Your brain has processed your emotions with the gentle wisdom of a skilled counselor, helping you maintain psychological balance in an often challenging world. It has explored creative connections between different pieces of information, like an inspired artist, potentially revealing new insights and possibilities that weren't available to your conscious mind. All of this work has been accomplished while you rested peacefully, protected, and sustained by biological systems of incredible sophistication and reliability. The sleep you have completed represents a small but essential part of the great cycle of renewal that sustains all life on Earth. Just as plants draw nutrients from the soil and energy from the sun, your brain draws restoration from the depths of sleep, emerging renewed and ready to engage with the world's infinite complexity. This process connects you to the fundamental rhythms of nature, reminding you that even the most sophisticated human achievements rest on biological foundations that have been billions of years in the making. As you move forward into your day, remember that the clarity of thought you experience, the emotional balance you maintain, the creative insights that may emerge, and the capacity for learning and growth that defines your humanity, all rest on the foundation of restorative sleep. The 8 hours you spent in slumber were not lost time, but invested time, hours devoted to the essential maintenance and optimization of your most precious resource, your mind. Your brain's nighttime work represents one of nature's most elegant solutions to the challenge of maintaining complex systems over time. Rather than allowing the wear and tear of daily activity to gradually degrade cognitive function, evolution has created a process that actually enhances and optimizes brain function through the gentle, restorative work of sleep. Each night brings not just recovery from the previous day, but preparation for greater achievements in the days to come. The neural pathways that were strengthened during your sleep now stand ready to support new learning and adaptation. The emotional circuits that were calibrated during REM sleep are prepared to help you navigate whatever challenges and opportunities await. The creative networks that were explored during dreams may surprise you with novel solutions and innovative perspectives. The waste clearance systems that operated throughout the night have left your brain tissue clean and optimized for peak performance. In this moment of awakening, you represent the culmination of an ancient and ongoing partnership between consciousness and restoration, between activity and rest, between the demands of the external world and the needs of the internal mind. This partnership has sustained human consciousness for thousands of generations and will continue to sustain it for thousands more. You are both the beneficiary of this evolutionary wisdom and its continuing expression, carrying forward the remarkable capacity for thought, feeling, and creativity that sleep makes possible. As you rest now in this moment of quiet understanding, having journeyed through the remarkable landscape of your sleeping mind, perhaps you can feel a deeper appreciation for the gentle miracle that unfolds each night within the sanctuary of your skull. Your brain, that 3-pound universe of infinite complexity, never truly rests, but instead transforms each period of sleep into an opportunity for renewal, restoration, and quiet preparation for whatever tomorrow may bring. Tonight, when you close your eyes and surrender once again to sleep's tender embrace, remember that you are not simply shutting down for the night, but entering into partnership with one of nature's most elegant and essential processes. Your neural networks will begin their ancient dance of maintenance and optimization, guided by millions of years of evolutionary wisdom that operates with a precision and care that surpasses conscious understanding. So rest peacefully, knowing that your brain loves you enough to work tirelessly through the quiet hours, tending to your memories, processing your emotions, and preparing your mind for all the wonders that consciousness makes possible. In sleep, you are never alone, but cradled by the gentle, faithful rhythms of your own remarkable biology.